In this subtopic, I will discuss a bit more detail about the proportional controller, the one that we just discussed, and another type of controller, the integral controller. Okay, let's start it with the proportional controller. As I mentioned before, why this kind of controller is referred to as a proportional controller, because the relationship between U and E is proportional, is linear. So as you can see in this equation, the relationship between U and E is proportional by a factor of Kp. Kp is later we'll call it as a proportional gain. So U is equal to Kp times E. Or of course, if you write it in a Laplace domain, it's also the same thing, because Kp is a constant here. So U in Laplace domain will also be equal to Kp times E in Laplace domain as well. So basically here, P action is just an amplifier. It's just to amplify the error to get the U, the action of the controller. Kp is adjustable, so this is the parameter of your proportional controller, the only parameter in this proportional controller that you have to design. Okay. So because the relationship between U and E in this kind of proportional controller is linear, whatever error that you will get in your system will have a linear relationship with the U here. So the shape of the E will be the same as the shape of the U, because it's just proportional, just a factor of Kp here. In a block diagram form, you can write your proportional controller into this kind of form. So this is just a partial drawing of your block diagram in your controlled system with a P controller, because normally you will have plant to be controlled here, and then this is your output. You will feed it back and you have a sensor here. Of course, if you have a unity feedback system, this part will not be there, and then you will have a unity feedback system here, right? So this is how we use a P controller in controlling our system. What is the advantage of having a P controller? In general, using a P controller in your system will improve your transient response. You still remember, don't you? In a system, you have two parts of output, transient and steady state. By improving the transient response, that means you are making your system response faster, because transient response will tell you how the system will react in time, how fast the response of your system. So transient is related to the speed of your system. So basically, introducing a P controller will make your system response faster. P controller will give another advantage by giving a better disturbance rejection. So the effect of external disturbance to your system will be minimized here. As I mentioned as an illustration before, the dust in your heat pump of your air conditioning system, that is one example of a disturbance in your system. And then by putting this P controller, you will also be able to minimize the steady state error. In other words, you can improve the accuracy of your system. But be careful, if you don't set the proportional gain, the gain of this controller properly, you might end up into an unstable closed loop system. So this is one of the importance of designing a proper controller. Okay, apart from proportional action, there is also what we refer to as integral action. It's pretty analogous to the proportional controller. If in proportional controller, the relationship between U and E is proportional, in this kind of controller, I controller or integral controller, the relationship between U and E is represented by integral relationship here. So U is equal or is proportional to the integral of E in this case, with a factor of Ki, where Ki here is the gain of your integral controller. So this is another type of controller. In a transfer function form, in a Laplace domain, the relationship between U and E is represented by this equation. Okay. So this is the third controller action. After the first one is on off, we discussed proportional. Now the other one is I controller, integral controller. Again, remember the relationship between U and E is represented by integral operation here. This means if the relationship between U and E involves an integral action, what does it mean? This means the action of the U here will be proportional to the integral of E. So if this is a plot of your error in time, your U here will be proportional to the area, enclosed area of the E there. The area which is formed by enclosing the E graph here with the horizontal axis T. So the one that I indicated by red area here is the area that is proportional to the U action of your controller. What does it mean? This means then it might be that even if the error is zero, what does it mean? When error is zero, that means your output is equal to the setting point, your C is equal to R. Your controller might still ask your system to run. Your controller might still ask the system that is controlled to run. Why do you need that? There are many reasons for that. One of the most notable reason of having an I controller is that using I controller, you will be able to eliminate the steady state error. Or in other words, by using integral controller, you can improve the accuracy of your control system even further. So if you want to improve the accuracy of your system, I controller is much a better choice compared to the proportional controller. Of course, because U, as I discussed in the previous slide, U is proportional to the area of E, not to the E itself. So if the E value does not change its sign on the graphic, U will increase and becoming larger and larger. Okay. But if the E value change the sign, so if the E value is oscillating within 0, so larger Ki might result in more oscillatory UT. Your system might be always oscillating, right? So this is few things that I need to mention about integral controller. But one thing that is the most important thing is that the main advantage of I controller is to improve the accuracy of your system even further. Okay. But in practice, normally we don't do I only. Normally we also combine it with P controller. So what you see here is a combination of proportional action and integral action. This is what we call as a PI controller. In Laplace domain, you can represent it like what you see in this slide. You can try to derive it by yourself. In block diagram, you can also represent it like you can see also in this slide. Why do you need to combine P and I? It's pretty straightforward. The answer is pretty straightforward because you want to get the advantages of these two controllers. You still remember we use I to improve the steady state performance, to improve the accuracy of the system. And in our previous few slides, we use P to improve the transient performance, to make the system response faster. So if you want to get advantage of these two, use the combination of P and I, PI controller, to improve the accuracy as well as to make the system response faster.